yeah, I'll start by thanking, I guess, Optima as a whole for inviting me to come and give a talk, well, remotely. And so I'm going to be talking about, large-scale derivative-free optimization with random subspaces. This is joint work over the last couple of years with Coralia Cartis, who's at Oxford, and Clément Royer, who's in Paris. You'll sort of see there's kind of two different streams of things. There's two papers that I'm mostly going to be talking about and two pieces of software. I'm not going to linger on this page. It's just there if you want to look that up for reference later. And I guess this is being recorded, but I'm also happy to share slides for anyone that's interested later on. So my plan is, and this may be fortunate for Peter, but I'm not going to assume a particularly large amount of kind of technical background in sort of optimization technicalities from a mathematical point of view. So I'm going to start off by introducing what derivative-free optimization is, and then jump into the subspace methods, the sort of the key new idea I want to talk about today, and hopefully have a bit of time to show a few numerical results at the end to see how well these things work in practice. But we'll jump right in. And basically, the area of optimization I'm going to be talking about is unconstrained nonlinear optimization. So all I'm going to be assuming is that there's a vector in Rn that I want to change to optimize some objective function f. And I'm not really going to assume very much about f. I'm going to assume that it's smooth, so it's nice and differentiable. But I'm not going to assume things like convexity or linearity or quadratic or anything like that. It's potentially going to be black box, so I'm not going to assume I have access to the underlying calculations that give me f. And in practice, I'm going to go even further and say I don't even need the actual value of f. I'm going to allow inaccurate evaluations, and that could come from something like, say, noise, if f is generated by a Monte Carlo simulation, or maybe there's some iterative process underlying the calculation of f that means that you can get a good approximation to f, but you can never get exactly the value that you want. And again, from an optimization point of view, what I'm going to really be looking for here is a local minimizer. So I'm not going to try and globally optimize a non-convex black box function. That is an extremely difficult challenge. I'm going to be content by finding a local minimum. And actually, from a theoretical point of view, I'm going to cheat a little bit and say I'm not really looking for a minimizer. I'm actually going to be looking for an approximate stationary point. So I'm just going to ask to find a point where its gradient is close to 0. And in a way that I'm going downhill. So hopefully that means that I'm at a good place. But as we'll see, the sort of context I'm talking about with sort of non-convex black box functions, realistically actually getting all the way to a perfect optimum is sometimes a bit of an unrealistic expectation. And in practice, I've found that practitioners and so on are often happy just with improvement. So given my current x, find me a different x that has a smaller value of f, even if it's not necessarily the best possible value. And as I'm sure most of you are aware, there's plenty of algorithms to solve this very general problem. The most famous ones I've tried to list here include line search, where we start at a current iterate, and then we take a step in, say, the negative gradient direction, or maybe we solve a linear system to get an improved direction. So that covers things like gradient descent, Newton's method, quasi-Newton methods like BFGS, and so on. Another approach is trust region methods, and this is the one I'm going to be talking about in more detail. And there you sort of go the other way. You first pick how far you want to go, and then you choose a direction. Whereas in line search, you pick a direction you want to go, and then you pick this step length alpha based on what works. So trust region kind of flips that order. But there are other approaches as well, which you may or may not be familiar with, but you don't need to worry because I'm not going to talk about them. But I will be talking about trust region methods. So I want to give just a very quick overview of how these work for those of you that haven't seen it. And the idea is that I've got a current approximation xk. So this is going to be my estimate of the minimizer of f. And what I'm going to do is say, well, f is a pretty complicated object potentially to work with. So I'm going to replace f with a model that's going to approximate f at least near to xk. It's not necessarily going to be a good approximation everywhere, but it should be a good approximation near to xk. And there's lots of ways you could imagine doing that. The simplest is probably to use a Taylor series. And typically speaking, we might want to use maybe a quadratic Taylor series that looks something like what I've got over here. And so what I can then do is say, let's replace my problem of minimizing f with my problem of minimizing this model m, because I've gone from this complicated black box function to a nice quadratic function where I know everything about it. So what I'm going to say is that I'm going to find a step that comes from trying to minimize this model, but I'm conscious of the fact that this local model, this Taylor series, is only really accurate if s, the perturbation s, is not too large. So I'm going to add in this constraint that says I want to minimize my model, but I don't want to go too far. I want to keep control of a parameter delta, and that tells me how far I'm allowed to go. And that's just acknowledging the fact that these models are only really suitable for small perturbations. But how small is not necessarily known in advance, which is why we allow delta to change as the algorithm progresses. This may look like a complex problem because potentially M could still be non-convex depending on the structure of the Hessian, but this has a lot of special structure that makes finding a good SK not too difficult. But once we've got that, we've found a new point, xk plus sk, and we think based on our model that this is going to improve the value of f because it's decreased our value of m. That's how we found sk. So hopefully it's going to decrease our value of f as well. So what we're going to do is we're actually going to check it. We're going to evaluate f at our new point. And if we got a nice decrease in f, then we're going to say, great, we're going to jump, and x plus s is going to be our new iterate. And in that case, we may want to increase the size of delta, take bigger steps in the future. If things went badly and we didn't get sufficient decrease, so our model predicted that x plus s would be a good place to go, but it turned out that that was not the case, then we're going to stay where we are. And the really important thing we're going to do is we're going to decrease delta. We're going to take a smaller step next time. And ultimately, this ends up working because as you shrink the size of your radius, your Taylor series definitely becomes a good approximation to your function, no matter what the function is. This is a very effective algorithm. This basic idea of shrinking your radius if things are going badly means you can prove all sorts of things about this algorithm. A simple result might be that you can prove that the gradients that you see go to 0 as your algorithm progresses. Now, that's all very well and good. This is an effective algorithm, but if we've got methods like this, and I've just put up my quadratic Taylor model and an iteration of Newton's method here, one thing that we need to do in order for this to work is we need to be able to not just calculate the value of f, but we need to be able to calculate its derivatives. So in this case, maybe it's first and second order derivatives, which leads us to a question of how are we going to do that? And there's generally a few different options for this. If you know the structure of f, you know the sort of mathematical formula for it, you can calculate its derivatives yourself, using high school or undergraduate calculus. You can write a piece of code that implements those functions and you're very happy and you're on your way. But if you don't know the structure of f, you can do things like finite differencing. So you can perturb f to estimate its gradient by perturbing it in different directions. Or in the more sophisticated side, if you have access to the source code that evaluates f, you can use techniques like algorithmic differentiation, or if you're a machine learner, you will call it backpropagation, that essentially uses the chain rule to take a piece of source code and compute, sort of semi-symbolically, compute the derivatives of f. And those are sort of the standard methods that you might want to use. But these aren't always useful. So as I've said, if you've got a black box function, if you don't know the mathematical structure of it, then you can't write code by hand. And generally speaking, you won't be able to use algorithmic differentiation. And so you're really left with finite differencing. But if on top of that, you have a function that's either noisy, so you don't have exact values of f, or maybe it's computationally very expensive, so calculating f given a single x takes a long time, then doing finite differencing is going to either be very inaccurate or take way too long for things to work well. And so when you're in this situation of sort of a complicated, expensive, noisy black box function, you can't really get derivatives of f in a reasonable way. And then you need to turn to something else. And that something else has the somewhat apt name of derivative-free optimization, DFO. And that's what I'm going to be talking about today. So why or how might this come up? So I've got just a couple of applications just to give you an idea of how this could arise. So the first one is some recent work I've done on climate modeling. And this was what on the face of it is a very simple problem. You've got a model that simulates the global climate, so atmospheric physics, oceanic physics, and so on. And that's got some unknown parameters. It's a PDE-based model. And so you might want to do parameter calibration by taking some observations and then finding parameters that fit those values. So that would be a standard least squares problem that people across the sciences do day in, day out. And ordinarily, this would never be coming up at a research level talk. The problem is in this particular situation, when you've got a climate model, generally speaking, one model run, one evaluation of f of x involves a global simulation of the Earth's climate for perhaps 5 years in this case. And that takes a lot of time. We're talking hours or days on a supercomputer just to do one model run. On top of that, the physics that's being modeled, the underlying structures that we're trying to deal with are extremely complicated. They've got chaotic dynamics. And ultimately, that means that we really don't know exactly what's going on. We've really got a genuine black box function. We can't use things like adjoint methods if you're familiar with those. And it's a noisy function. If you perturb your parameters slightly, you can end up in a very different place because of the chaotic structures. So you really hit all three, black box, expensive, and noisy in this case with this, what would otherwise be a very simple parameter fitting problem in this climate context. A different one from a more data science point of view, I know you've had a few talks more on that side of things, is generating adversarial examples for neural networks. So we know neural networks can be very good at classifying images, for instance. The idea of adversarial examples is to say, here's an image, for instance, that's classified well by a particular neural network. Let's see if we can perturb it essentially imperceptibly. And I've got an example here where we've got an image of a panda that we make a very small perturbation to. And note there's a sort of an epsilon in front of it so that the changed image looks essentially the same as the starting image, but we've perturbed it in a very structured way. That means that the high quality, the well-trained neural network ends up completely misclassifying the image that we've been given. And this is, again, if we don't know the structure of the neural network, this is a complicated black box problem of how do you find these perturbations. And particularly if you're looking at adversarial examples, if you don't know the structure, you may want to essentially do this undetected by doing very few queries of your neural network. And essentially, although neural network evaluation is not very complicated sort of in terms of computational cost, if you want to test very few examples for practical reasons, sort of say to remain undetected, then essentially we could model that as an expensive evaluation. So those are just two examples of why this sort of structure might arise. But now I want to do is dive in and ask, how do we go and solve optimization problems without derivatives? How do you go uphill or downhill when you don't know which way is up or down? So there are two types of algorithms I'm going to be discussing. There are others that exist. The first one is called model-based, and it's called model-based because it really relies on this whole trust region framework where we build local models. It just does things in a slightly different way. So we're going to sit in a trust region framework, and exactly the same, we're going to approximate our complicated black box function by a local quadratic model, except now I've replaced the gradient and the Hessian with a vector G and a matrix H, and I don't know what they are. And essentially, I'm just going to say, find me a G and an H without using the derivatives of F. So don't use the gradient and the Hessian, do something else that doesn't use derivatives to find them for me. And the way that we tend to do that is to use interpolation. So we're going to collect a set of points, and these points are generally speaking going to live near xk, and we're going to require that our model predicts the value of f correctly at those specific points. And that will give us some equations we can use to find values of g and h. Now, in order for this to work, so mathematically speaking, the main condition that we need is our model has to be an accurate approximation for f. Previously, we could rely on Taylor's theorem to tell us how accurate our model was. Here, we don't have that. What we require for this to work is that our model has to be a good approximation of our function, in that as we vary s within a distance of delta k, remember that's how far we're looking, the difference between the function, the true function, and our approximation has to be at most error of size delta squared. But we also need it to well approximate the gradient of f as well. So the difference between the gradient of the true function and the gradient of our approximation, again, also has to be small. But if delta is small, it's a slightly weaker requirement. Now, this may not be particularly intuitive, but essentially we need our interpolation model to still be a good approximation. And this is achievable if our interpolation points, this script y, are well spaced throughout our space in a particular way that I'm not going to go into details, but you might want to imagine that you don't want all of your points lying on a line or something like that, because then you're not seeing how the function varies outside of that line. So that's the basic idea. It's much easier to illustrate with a picture. So I'm trying to minimize the blue function to find the red point. I've evaluated f at these 3 points in black, and the one with the big circle over here is my current iterate, because that's the best point I've seen so far. And so the trust region I'm going to search for is my current iterate, but then take a ball around that of a certain width, delta. So I'm going to pick some interpolation points. I'm then going to fit a quadratic to those 3 points. So I'm fitting a quadratic function in 1D, so I only need 3 unknowns to do that. And so I've interpolated my function. I'm now going to minimize the black line, which I know, inside my shaded area, inside my trust region. And that's going to say, I want to go to the right. I want to look over here. So I'm going to go over there. I'm going to evaluate my function, see how well I did. Did I decrease compared to what I was hoping? And the answer is yes. The decrease in the black line and the decrease in the blue line are pretty good. So I'm going to say, this is a good point. I'm going to move over here. But that means I need to get rid of an old interpolation point if I want to keep my 3 points that I'm actively going to be working with. There are ways to do that, but in this case, I'm just going to throw away this point on the left here that I've circled in red. And if I do that, update my radius, I get a new set of points, which gives me a new quadratic model in black. Again, minimized to the right-hand side. Is this point good? Well, it decreased the function, not as much as the model, but still a pretty good job. So I'm going to jump over here, throw away an old point, and repeat the process. Now I get a bit of a difference. If I minimize my quadratic model, I end up again moving to the right. But now my function has gone uphill, where my model has gone downhill. So this was bad. I'm not going to take that step. I'm going to stay where I am stay at this point in the middle, but I'm going to shrink my radius. But I am still going to add this point to the interpolation set because although it didn't improve my function, it does give us an idea of where not to go. So there is still useful information. So I'm going to add in that new point. And now I've got an approximation that's very good. If I minimize it, I basically end up with the solution. So that's the basic idea there. We're kind of taking what we would do in a traditional nonlinear optimization framework and essentially replace Taylor series with interpolation functions. A completely different, but sort of conceptually simpler idea is what's called direct search. So this is a very different optimization method, but it proceeds again in an iterative manner. So I'm going to start with a starting point, my current starting point, and my radius or my distance. But what I'm now going to do is, instead of trying to build a model, I'm just going to build in some way, construct a set of vectors. And I'm not going to tell you exactly how I'm going to do that just yet. But I'm going to just choose a collection of vectors. And then I'm going to go through my set of vectors and evaluate xk perturbed by that direction, d, with a certain length, delta, and say, if I evaluated any of those perturbations, do any of them improve on where I am currently? Do they decrease f compared to my current best estimate, at least by a certain fraction that depends on delta? There's an extra term we require a bit of buffer. If in my set, there's a direction that gives me a perturbation where I decrease f, then I'm very happy. I'm going to move over here and I'm going to increase my step size. This is very similar to trust region. If I went through my whole set of vectors and none of them decreased f, then I'm going to stay put and I'm going to decrease delta. Same sort of reasoning there, but we're just constructing our points to evaluate, the points to check in a very different way. And in this case, in terms of the mathematical requirements, what we need is this dk, this collection of vectors, to be what's called kappa descent. And that's the equation for it there. But essentially what we're asking is for any vector, in particular the negative gradient, but essentially for any direction we could ask for, there's a vector in this dk that has an acute angle with the vector of interest. So an acute angle with the negative gradient. And so there are plenty of ways to do that. An easy example is to use the positive and negative coordinate directions, for instance. Another way to do it is to take the positive coordinate directions and then the vector of all -1s. Those are two ways where if you pick any direction, one of these vectors will form an acute angle with that direction that you choose. And they give particular values of kappa. So again, this is much more easily illustrated with a picture. So in this case, I'm now working in 2D. I'm going to start at the blue point, and you've got the level sets of my function as I'm trying to find the red minimum. So what I'm going to do is I'm going to start at my blue point, my xk, and I'm going to check xk plus or minus all the coordinate directions. So this is dk being plus or minus e1 plus minus e2. So I'm going to start at xk and perturb in each of those 4 directions by length delta k. And I'm going to check if any of these values, if any of these points give a smaller objective value. And in this case, the one I've denoted with a star improves on where I was. So I'm going to jump there now. And again, I'm going to sample those plus and minus coordinate directions and see if there are any good points. But I'm now searching a little bit further. Things are going well. This point's the best of those ones. So now I'm going to look over here. And again, do any of these points improve on where I was? In this case, no. These 4 perturbations all give worse values of f. So I'm now going to shrink and check that points that are closer. And that gives me the new value up the top here. And we found a lovely good point there. So we're going to jump over. And again, we're going to repeat this process. And we're slowly going to end up at the red point. So the trick is we need to find this set of directions where we can essentially always guarantee we've got something that makes a good angle with the negative gradient, which means there's essentially a descent direction floating around. Now, from a theoretical point of view, and this is sort of the, let's say the theoretical question I'm sort of interested in for this is what's called worst case complexity. So I'm going to say there's a particular error tolerance I care about that's epsilon. I'm going to say if I want to get a point with a small gradient less than epsilon, how long do I have to wait? How long does it take me to achieve a certain level of optimality in terms of the level of optimality I'm asking for? And there's a couple of different metrics you could use. You could either ask how many iterations of my method do I need, or how many evaluations of my objectives. This is evaluations of f. And just to kind of give you an idea of how this works, I've got 3 columns. So derivative-based methods. So this might be classic trust region or line search methods. So classic methods with derivatives, and model-based and direct search derivative-free methods. And the sorts of results you get, all of these say if I want optimality level epsilon, it's going to take me about epsilon to the -2 iterations or evaluations to get that. That's essentially can't be improved in this with these sorts of techniques. You've got to do things that are slightly more advanced to improve on that. But the other thing that's interesting is the dependency on n. So this is the dimension of the problem, the number of unknowns I'm trying to find. And what we see is that the coefficients of n, they're the same in model-based and direct search, but they're all a fair bit higher than what you get in the derivative-based case. So what, generally speaking, we can say from a theoretical point of view is that once we remove derivatives, we're losing information. And in terms of the algorithm complexity, this means things are basically going to take the same length of time in terms of epsilon. But as we increase the dimensionality of our problem n, these DFO methods are going to slow down much more than derivative-based methods will. And to add just a little bit on top of that, model-based DFO also has a fair bit of linear algebra work in every iteration, and that's something in the order n cubed flops per iteration. So in all of these cases, if n gets large, these DFO methods start to trip up and start to fail. And so the challenge that I've been trying to address with these new methods is to how to make this more scalable. How do I remove as much of this dependency on n as I can get? How do I make things better if n is large? And just to show you where I'm going, this is where these new methods are going to end up. So we're not going to be able to improve on the iteration counts of model-based and direct search methods. But in terms of evaluations, we're able to drop from n squared down to n. And roughly speaking, that's sort of comparable to derivative-based methods if you think of finite differencing. So that's makes things a lot closer to what we might hope. And the other benefit that we get is the linear algebra work also decreases substantially. So 2 orders of magnitude, we can get a reduction there. So fewer evaluations and less linear algebra work is where we're going with this. Okay, so let's have a look at how we might do this. So very quickly, people have been looking at this issue of scalability in various ways. A lot of things around exploiting problem structures in specific instances. And a technique that machine learners like to use is sort of a randomized finite differencing or gradient sampling approaches, they call it. And that then can fit within sort of a more machine learning framework where they can do things like classic gradient descent and so on. And in terms of applications for scalable DFO, we might be looking at machine learning. I've done some work in image analysis where higher dimensional DFO could be helpful, and potentially as a proxy for global optimization methods as well. Because global optimization has a very fundamental dependency on n that you can't get rid of, but they also tend to be derivative free. So maybe these local methods could sit sort of in between as a way to kind of give us some degree of global optimization in higher dimensions. So one approach that is fairly promising is essentially based around randomization. And there's some work by a few different people, including my collaborator Clément, that essentially looked at taking these DFO methods and adding randomization. So instead of saying at every iteration, I'm going to have a lovely accurate interpolation model, or I'm going to have a lovely choice of search directions in direct search, I'm going to say I'm only going to ask for these things to happen with some probability less than 1. So at those other iterations, things might not go very well. I might have a poor quality model. I might have a set of directions that's not descent, and essentially convergence guarantees disappear on those iterations. But if your probability is not too small, you can still make progress. And the key upshot of those 2 papers are if you do that for direct search, you actually get what we were hoping for. The n squared complexity becomes n. But if you do it for model-based, that doesn't happen. You stay at n squared, which leads to a really kind of odd gap. These methods, from a theoretical point of view, often sit very similarly, very close to each other. So why, if we just insert probabilistic ideas in there, does one of them improve things and one of them not? And the basic idea is that direct search essentially allows you to do dimensionality reduction in the sense that you're sampling much fewer than n directions. To do probabilistically fully linear models, you don't really have the same approach. So essentially what they do in direct search is say, well, instead of searching, in all my coordinate axes, just pick a random direction and maybe it's negative. And that's not kappa descent, but it is kappa descent for a lot of iterations. So the new goal is really to use dimensionality reduction techniques that are going to work for both DFO classes. And the key mathematical tool that we're going to use to do this is what's called the Johnson-Lindon-Strauss lemma. Now, this is having a lot of applications at the moment from sort of a data science point of view. It's underlying things like randomized linear algebra techniques and all sorts of things. So I want to just state it here, just to, if you haven't seen it, this is a really kind of interesting mathematical result that has is getting a lot of applications, particularly in a data science area. So this is an older result. It's from the 1980s, and it wasn't quite phrased in this way, but this is sort of an analogous framing of the result. And so what I'm going to ask for is I'm going to pick capital N points living in RD, and my ambient dimension D I'm imagining to be very large. So I've got a collection of points in a high dimensional space, and I'm going to pick some error tolerance epsilon. And what I'm going to do is I'm going to generate a matrix A, and A is going to be sort of a short and fat matrix, so P rows and D columns. And the idea is that P is going to be much smaller than D. And I'm going to generate that randomly. So the entries of this matrix A are going to have just independent Gaussians. We're just going to draw randomly distributed normal values and fill the entries like that. And we're going to pick a particular value of P that depends on my error tolerance epsilon and the number of points I'm interested in handling N. And what happens is we're then going to look at the map. Instead of dealing with sort of things like X and Y, they're going to live in RD. I'm going to instead hit all of these vectors with the matrix A. So they're now going to live in a smaller space, RP, in a lower dimensional space. And the key result is that structure is preserved. So in this case, the distances, the pairwise distances between all the points is preserved at least up to some small error tolerance. For any two of my points, I preserve the distances between them, which means I preserve things like angles, lengths, and all sorts of structure that you had in your original point cloud. And the really kind of powerful thing, aside from it being easy to generate A, is that the dimension that you're projecting down to goes something like the log of the number of points you want to handle. It doesn't have anything to do with how high dimensional your vectors started with. D could be as large as you like. That doesn't matter. You can always project them down to a very small dimension that's the log of how many points you have, independent of what dimension you started in. And that's why this result is particularly powerful as a dimensionality reduction technique. So I've said a lot of these things already. We preserve distances and various other sort of geometric structures of our points. Our lower dimension depends only on the number of points, not the dimension that they started in. And I've just used Gaussians. There are other constructions that are randomized that also satisfy this requirement. I'm not going to talk about those. So what we're going to do is we're going to use this idea in our optimization algorithm to essentially generate subspace methods. And the way we're going to do that is we're going to search in low dimensional subspaces of Rn. So instead of starting with an xk, trying to find an xk plus 1 by looking at essentially everywhere in Rn, we're going to say we can only move to our new point inside some low dimensional subspace. So this is somewhat similar to coordinate descent, which is a popular method in data science, where you only perturb some entries of X each time. People have looked at implementations of these ideas, but there's really not been very much theory until some more recent analysis in the derivative-based case. But this is the basic idea. I'm going to say, instead of searching for everything in Rn, I'm going to generate a subspace of much smaller dimension by looking at the column space of some matrix that in this case is tall and skinny. You can think of this as the transpose of my Johnson-Lindon-Strauss map. And then what I'm going to do is essentially do my existing DFO method inside this subspace. So in the model-based case, I'm going to look at this function of a low dimensional variable s hat. Essentially, we're only going to care what's happening in this sort of affine space generated by our projection. And we're going to build a model for this function. So a model for this low dimensional function in exactly the same way we would for a high dimensional function. And again, for direct search, I'm going to choose a set of directions in my small dimensional space. And I'm going to ask that it's kappa descent not for my full gradient, but for the projection of my gradient into my small dimensional space. So everything just kind of goes down into a subspace. We do our one step of our algorithm, and then we pick a new subspace, and then again, do the same iteration again. And the basic benefit of all of this is we don't need as many interpolation points. We don't need as many sample points. Our linear algebra becomes cheaper, essentially because we're doing everything in a low dimensional space. The cost of everything comes down. So how can we get this to work? We can't just choose any subspace, unfortunately, if we want to optimize. We really need to be searching in good subspaces. And when I say good, I mean that there is enough scope for us to decrease f inside this particular subspace. And in order for that to work, I need to ask something about my random map. And what it says is if I project my gradient into my subspace, that I at least retain some fraction of that information. There's at least some gradient, some non-zero gradient in my subspace that I can find, which means essentially, if there's still work to do, if our gradient is large, then we can see that extra work only by looking at how f moves in the subspace, because essentially its subspace gradient is also large. So that's what we're going to ask for. And if we can do that, then everything's going to work beautifully, and our subspace method is going to work. The problem is that's not quite so easy to do because we've got these random constructions. So instead, what I'm going to ask for is this property to hold with some high probability. 1 minus delta. And where we really get the benefit is we can use Johnson-Lindon-Strauss, and that says that the dimension that we have to project into can be chosen independently of the dimension of the space we're working in. So how far we project down essentially is order 1, independent of the dimensionality of our original problem because of the nice properties of these JL constructions. Just for comparison, if you were to randomly select P out of your n coordinates, so P out of your n entries of X, and only perturb then actually you do need P to be a certain fraction of n. If you want to get 10% of the gradient, you need to sample 10% of the coordinates. So we can't just do random coordinates for this to work. We need these JL constructions that do a lot. They're a lot more complicated that enable this order 1 outcome. So that's the nice idea. And then once we put it all together, and again, I'm not going to go into details, but the sort of result we can say is that if we want to achieve optimality level epsilon, then I'm going to have to wait for k epsilon iterations. And k epsilon is going to be order epsilon to the -2, which you've seen earlier. That's the standard size that we expect that to be, but with some constant that depends on our algorithm. But instead of that holding all the time, that's going to hold with some high probability. And as epsilon goes to 0, that converges to 1. So that is a very high probability if we're looking at high accuracy. And ultimately, we can prove a variety of results like bounds on the expectation of k and various other things. The other really important thing is that the number of evaluations per iteration is no longer order n. We don't need to sample n points or 2n points, let's say, if we're doing direct search, in order to check everything that we wanted. Because we're working in a subspace, we only need to look at order p points. And remember, p is going to be order 1. So the amount of evaluations we need to do per iteration is drastically reduced compared to the standard case. And this is for both the model-based and direct search framework. So just to summarize where we end up, this is the table I showed you earlier, and our improvements are down here. So the number of evaluations required, the dependency on n reduces essentially from n squared down to n, and roughly speaking, compared to finite differencing, we're basically matching that result. And as I said, the other benefit is because we're doing all the calculations in our subspace, our linear algebra work for model-based methods, which can be significant when n is large, drops down quite dramatically as well. So we get these sort of dimensionality reduction techniques coming from data science. If we essentially work in these random subspaces of each iteration and we redraw the subspace each time, then these n dependencies can drop down, essentially because we're working in subspaces, but they're well-chosen subspaces. They give us really nice properties. How long have I got left? Someone... it's about 1:45. How long do you usually
you can go to at least 5 minutes before we'll have some time for questions, so don't be too stressed. Okay,
sounds good. So yeah, in terms of the numerical results, that's sort of the theoretical analysis that basically says subspaces are an idea worth having. There's 2 open source Python codes that I've got up on GitHub that you can have a look at. The first one is this subspace model-based method, but specifically looking at the problem of nonlinear least squares, so essentially parameter fitting type problems. So we've taken this basic subspace idea that I discussed the theory of and added a whole bunch of heuristics that improve kind of the practical performance. On top of that, we don't have a code for general f of x yet, because in order to get that to work efficiently, and I'm thinking with these extra heuristics, is a lot less straightforward. So that is a watch this space type thing. On the direct search side, we have package, which we've aptly called direct search, and that implements a whole bunch of these different methods. So the classical, randomized and subspace methods, many different ways of generating your descent sets and so on. So a very flexible package. But these are the sorts of results I wanted to discuss. So for these plots, what I'm essentially plotting on the x-axis is computational effort in terms of number of evaluations. So it's sort of normalized essentially by problem difficulty. But so the x-axis is essentially number of evaluations. And on the top we've essentially got percentage of problems solved. So basically, you want to be sort of on the top left as far as possible. You want to solve more problems more quickly. So this is comparing our model-based subspace code with an existing code I've got that does regular non-subspace methods. And basically what we see is as we increase P, we head out in the better regime. So essentially, as our subspace gets bigger, we end up approaching the full space methods, and the full space methods are the ones in gray and black. And if we go all the way out to P equals N, we essentially match that performance. So what this is basically saying in practice, and this is for low accuracy problems, is the larger P gets, the better you'll perform in terms of number of evaluations, which is unfortunate because we want to set P to be small. We want it to be order 1 for things to work effectively. But what happens is if I go from these problems, which I would say from a DFO point of view, a medium scale, 100 unknowns, and jump over to 1,000 unknowns, these two plots look extremely different. And what we get is that these codes, particularly once we get up here, we can end up outperforming these full sort of P equals N codes that are sitting over here and solve a good fraction more problems by working in very small subspaces. This is, P is order 10, I think, for these problems. And that's because in order for this to work at all sensibly, I had to impose a timeout on the solver for every single problem that I tested. I gave it a generous 12 hours. And in this case, function evaluations essentially cost nothing. This is really because of the massive linear algebra cost of these model-based methods, that once I start increasing N, I just stop making progress. I can get a certain level because large P's tend to work, which is what the left-hand plot shows. But eventually this timeout just kills you. And ultimately, at some point, you might want to switch to cheaper, low-dimensional methods like the purple line here. So again, for large-scale problems, these subspace methods can be practically quite helpful where they aren't in the small n regime. From a direct search point of view, things are a little bit trickier because there are already existing methods, these randomized methods that had strong performance. But again, just to give you an idea, classical methods essentially are sitting kind of the gray and black line. So these are sort of the P equals N case up here. And up here are the sort of P equals 2 methods, the low dimensional random subspace methods that, again, are massively outperforming these classical methods. In this case, even for lower dimensional problems, we still get a significant improvement. And we see exactly the same improvement for large N as well. Using these subspaces is as good as, or in some cases, can still outperform the randomized method to have the same improved complexity. So that's randomized, and up here we've got subspace. So both of these have the same improved complexity, but the subspaces can still be an improvement. I haven't directly compared the model-based and the direct search because in practice, model-based does tend to outperform direct search quite a lot, just as a general framework, because it's more adapted to how the function works. It's a bit of a more complicated method. So I've sort of separated the two comparisons out of fairness. So these two slides hopefully give you some idea that actually these subspace methods can be useful in practice as you get to these larger dimensional problems. An alternative benefit that you can see, and it's much more visible on this left-hand plot, is if you've got extremely small budget, which in this case, I'm allowed up to n+1 evaluations. And remember, if n is large, that's not necessarily a small budget. And if you've got things that are computationally expensive, you may well be at a much lower budget down here. If you've got a very expensive simulation that you might want to run, you might not even be able to do enough evaluations of your objective to get a single gradient out where you need order n. You may need significantly less. And the advantage of these subspace methods is that they only need essentially sort of order p startup cost. So the amount of time it takes them to start making progress is substantially smaller than the number of unknowns, which if n is large and you've got very few evaluations to work with, can mean the difference between making some progress and making no progress at all. So that's sort of an alternative way of thinking about it. If you've got expensive objectives, actually these order n things that people talk about in DFO world as number of evaluations becomes completely useless. And again, this is much larger evaluations, but again, for small budgets, we can, again, with these direct search methods, get very rapid improvements compared to the other techniques that exist out there. Okay, so that's where I think I will leave it. In terms of the key points I want to take away, so we've got these DFO techniques that are very useful. I should cross out model-based up here. For sort of expensive black box functions and so on, they are very effective in practice, but their scalability, if you've got a lot of unknowns, is limited both in theory and in practice. But things like the Johnson-Lindon-Strauss lemma, these randomized projections, can be very good dimensionality reduction techniques. And once we incorporate those in, we can get new algorithms with cheaper linear algebra, cheaper iteration complexities. They work well in practice, and we can take a big step forward at increasing the scalability of these methods. Now, there's a whole bunch of directions that we want to keep going with this. We want to look at sort of second order complexity analysis. So from a theoretical point of view, that's asking that our gradient is small and that the eigenvalues of the Hessian are close to 0 or positive. So the Hessian is approximately positive semi-definite. So looking at second order optimality conditions. As I said, we don't have a model-based method for general objectives. We want to figure out how to do that efficiently. We want to add in constraints. We want to look at explicitly what happens if there's noise and uncertainty in the valuations of F. And there's actually sort of a stop the presses thing I added in today. There's a work paper that came out about 2 weeks ago that starts to look at that in the model-based context. So anyway, that was everything I wanted to talk about. And yeah, I'm happy to take any questions you might have for the next sort of, I don't know, 5-ish minutes. I think I've got a couple more minutes.